So now let's learn of some set theoretic operations on finite automata themselves. For example, in sets we have the concept of a complement, right? For example, imagine this is my universal set and this is my set A. What is A complement? A complement is everything that is outside of A but that is within U, right? In other words, A complement, which is also written as A dash, is nothing but U minus A in set theory. Similarly, we can also construct the complement of a finite automata. Let's understand this concept from an example. Imagine if I have a finite automata or a machine M which is like this. Okay, my alphabet here is A and B. My language that is accepted by this machine M is the set of all the words such that the word starts with A. Okay, that's what this automata does, right? Look at this. This is my starting state. If I have a transition A, I go to a final state. After that, whatever alphabet I get or whatever symbol I get, I'll stay in the final state. But if my first character is B, I end up in a dead state. So if you notice this is actually a dead state, right? So this automata, now if I want to compute the complement of this automata, right? So let's start. So the complement of this automata is often written as MC or M complement. So this is what a complement of the finite automata is. But what does the complement here logically mean? Right? In sets, it's very simple. So can we use the set theoretic concept to define what the complement of a finite automata means? Yes. We can use this language accepted by the automata to define the complement. So the language accepted by M complement is all the words that are there in sigma star, in the clean closure of sigma, minus the words that are there in M. Okay, or the words that are there in language accepted by M, to be precise. Okay, so the language accepted by the complement of M is all the words. So if you think about this, if this is your set of sigma star, which is your universal language, right? If this is a set which is LM, right? This is the language which is all set of all the words that are accepted of machine M, then I can define the language M dash or the language accepted by machine, the complement of A. So the complement of M, which is called as M dash, is sigma star minus LM. Right? I hope this is clear. So everything outside of this, this whole region here, this is often written as, this whole region is represented as L of M dash, or sometimes this is also written as L dash, just as a short form. Right? Now, given that this is the language, how do I construct the automata corresponding to it? That's actually very simple. It's actually very, very simple. So if you think about this, my language, so a very simple way, given this language, I want to now write the automata corresponding to it. I can just take M, using M I can construct it. Here are the steps. Whatever are the steps, I'll continue to have the same steps. Right? Look at this. Everything stays the same. Look at this. This is my Q1. This is my Q2. There are a couple of things that change. My transitions don't change. My transition stays the same thing. Look at this. My transition stays the same. Right? My initial state does not change. Okay, the number of states don't change. The most important thing that changes here is all the non-final states here, which means this and this, they become the final states. All the non-final states here, because this is the final state here, all the non-final states become the final states in, so this is my M complement or M dash. Okay, this is my machine now. Okay, this machine, the starting vertex or the starting state doesn't change, or the initial state doesn't change. The number of states does not change, right? Look at this. Whatever are the non-final states here become the final states. The transitions don't change. The transitions also don't change. That's the beauty of it. And very importantly, if you notice here, we had a dead state. The dead state became a final state here, or an accepting state, right? So very interesting. This is how given a finite automata or a mathematical model M, you can compute its complement. Again, the complement itself is defined through the language, because the language itself is a set, and we have the concept of complements of sets, right? So all this derivation, all this logic flows through the complement of this set L, which we can call it as LM dash or L dash for short. Now, once we have this language, we can construct the automata corresponding to it. And it's very simple to construct it. Now, you might wonder, why do we need this? There are actually a lot of interesting problems that we can solve using this concept. Because in some instances, drawing or computing or arriving at the automata is easy. And if you want to actually obtain at the complement of it, you arrive at this. Let's actually see some examples. Okay, imagine I have this question. Construct a minimum finite automata that accepts all strings that do not contain AB as a substring. Look at this. We have seen in the previous videos how to construct minimum finite automata that contain AB as a substring. Right? We want all the strings that do not contain AB as a substring. So we know how to compute a model M that accepts, so if this language is L dash, look at this, if this language is L dash and the corresponding model is M dash, we know how to compute a model M that accepts L, which is the complement of L dash. Remember, fundamentally speaking, complement of a complement is the language itself, because complement of a set itself is the set. Again, remember, a language is nothing but a set of strings. Right? Language is nothing but a set of strings, and a language is a subset of your universal language, which is sigma star. So sigma star is behaving like a universal set. Right? And what we are doing here, the complement operation itself is like a set subtraction operation, if you want to think about it from a set theory perspective. Right? So now given this, first let's construct L and M. L is basically, now what is L now? Let's write down what is L. L is the set of all the words such that W belongs to sigma star and W contains, okay, so let me write this more properly. Okay, so it is a set of all the words W such that W belongs to sigma star and W equals to, it contains AB as a substring, X, A, B, Y. Okay, again here X belongs to sigma star and Y belongs to sigma star. Right, this is the definition of L. What is the machine corresponding to it? We have seen this, right? In many previous videos, we have seen the machine corresponding to it. How can I draw the machine corresponding to it? It should have AB as a substring. Okay, so let's actually construct that AB part first. A. So if I reach here, I've seen an A. If I reach here, I've seen a B. Okay, so this is AB. Okay, so after I've seen AB, whatever I see, I don't care. Very good. Now if I start with B, right, because it's substring, it says that constrain AB as a substring, right? So B will be here. Now this A, this B is done, this B is done. If I keep seeing A, I'll stay here. Again, we have seen how to construct this in the previous videos, right? When we learned the basics of how to construct automata. Cool. So we need 3 states. This is the automata. Now how do I now take the complement of it? Very simple. My complement of this L dash is set of all the words which do not contain AB as a substring. So how do I write M dash now? Very simple. Draw everything exactly as is. Right? Don't change anything. The transition stays the same. Okay, let's actually start drawing this. Right? My initial state stays the same. My transition stays the same. Right? So this is my B, this is my A, this is my Q2. Okay, so this is my AB. Okay, all the final states become non-final states and all the non-final states become final states. That's it. That's it. So this automata now, again, if you notice, this is a dead state now. Once you reach this state, you can never reach we can never reach one of the final states. Right? So given M, we can compute M dash very easily using, again, this is very easy because we learned how to compute the complement of a finite automata. This is a very nice example. Sometimes instead of building this automata directly, it's easier to build a complement of it. Once I get the complement of it, I'll again take the complement of it to get the automata that I want to build. Right? Very simple example. Let's look at some more examples like this. Suppose if I want to build an automata that accepts strings that do not end in BAA. That do not end. So let that language be L dash and the model be M dash. Okay, we'll construct that. Okay. So first let's construct L and M. L basically is strings that end in BAA. Right? So this is basically all the words which are equal to X BAA such that X belongs to sigma star. Right? Again, I'm assuming the alphabet by default everywhere is A comma B. That's the default assumption here. Okay, so how do I draw the machine for this? Very simple. We've seen the machine. We've seen how to draw the machine corresponding to it in the previous videos, right? So I start with Q0. I want BAA, right? So let's say B, A, and again A. Okay, this has to be my final state. This is Q2, this is Q3. So we accept BAA. Very good. So if I get anything before that, if I get A here, I continue to be here. Very good. Now what about this? A transition is there. What about B transition now? B transition also, I will be here itself. Okay, because I've already seen one B, I can see two more A's. Yes, we have seen all these cases, by the way. So now if I'm here, I've seen BA. If I get another B, I can transition here, because BAA is also final. Very simple. Now what about this? If I've seen, suppose if I'm here, okay, so BAA, if I see a B again, look at this, if I see a B again, I should go back here. Okay, if I see an A again, I have to go back to this. Okay, so this is my automata. This is my M, right? Very simple. What will my M dash look like? Very simple. Just draw the same thing. Just draw the same thing. Make your, okay, again, let me just draw it quickly. Q0, Q1, Q2, Q3. This is actually very, very simple. This is a final state, so this becomes a non-final state. These three are non-final states, so they become final states, right? So my A, the transitions don't change, right? B, A, A. And then B here, right? This A here, sorry. This should be B. I'm sorry. This should be B, not A. My bad. This should be B and this should be A. That's it, right? That's it. Okay, let me write it clearly. This should be A here. So B, B, A. Yes. So this B, because once I get a B, I can get AA. Once I get a B, I can get A. Yes. That's it. This is my M dash now. And the language accepted by this is simply the complement of this. See how sometimes just complementing things is extremely useful, right? Very simple examples. Now, just like complement, there is also another concept called as compound automata. So a compound automata basically means constructing unions of automata and intersections of automata. Unions and intersections. For example, imagine I have a language L1. Again, it's very easy to define unions and intersections from the context of languages, because languages are sets, right? So imagine if I have a language L1, right, and I have a language L2 and a language L3. I can easily define L1 union L2 union L3. Similarly, I can define L1 union L2 union L3. Now, corresponding to each of them, if there is a model, if L1 is a language accepted by M1, if M2 is a machine that accepts L2, if M3 is a machine that accepts L3, I can also define unions and intersections of models. That's what is called as compound models. Okay, that's the core idea here. Again, remember, this notation itself is incorrect. Because what does this mean? What is a model? A model is a quintuple. Mathematically speaking, a model is a quintuple. So this notation is not appropriate. So this is not the perfect notation. So this is notationally incorrect. I understand that. Okay, but you'll see some textbooks and articles which also use this. Because for a quintuple, how do you define intersection? But on languages, you can define them, right? So typically what people do when they write this is a notational, this is also notationally incorrect. But what this means intuitively is, we want a machine M. Let's say this is equal to M. Let's assume this is equal to M dash, which means we want a machine that accepts a language which is the union of all of them. Similarly, we want a language L dash. Okay, let me not use the word L dash here, because you might think of it as complement now, right? So let's call it L1, M1. Okay, if the intersection is L1, then this model intersection can also be written as M1. But this is not notationally correct. It is notationally incorrect. This is notationally correct because these are sets. But I've seen people use this also. If you see this, what it means is this. Okay, just to be clear here. You might encounter this notation also. While rigorously, if you talk about very mathematically, this notation is incorrect, but you might encounter it. Okay, because some people do use this. Okay, with this, now let's actually go into the details of it. Actually, the best way to learn is through examples. Okay, so let's actually look at this example. If I want an automata which has words such that, again, my alphabet is A comma B, my number of A's is even. So I use this hash as a short form for number, very popular in mathematics. Number of A's is even and number of B's is even. Number of A's is even and number of B's is also even. Look at this, I have and. So imagine if this is language 1 and this is language 2. We want something which is in the intersection of both these languages. Okay, in other words, if I build a model here and if I build a model here, I want to be able to combine these two models through intersection operation. Okay, first let's construct the M1 corresponding to it. Okay, so let's construct the M1 and M2 first. And we have seen how to construct M1 and M2. Then we'll come about how to build the intersection of both of them. Okay, so we'll break it down step by step. First, let's build M1. Okay, so what is M1 now? M1 is even number of A's, right? So 0 will be there. This is Q0. So even, odd. Okay, this will track even, this will track odd, right? So this is my B. I only care about A's. My B is here, my A will be here. Okay, so this is my M1. What about my M2? M2, number of B's is even. Very similar model, right? So instead of using Q0, Q1, let's use a slightly different Q2, Q3. Okay, again, Q2 is the initial state and the final state, right? So this tracks even. This is my odd, this is my odd Q3. And if I get a B transition here, this is this, this is this. Okay, because I want number of B's to be even. I have these two models. Now I want to construct a language which is the intersection of L1, L2. How do I construct that? Let's call that model as M. Now the big question here is, how do we construct that M, which accepts L1 intersection L2? Okay, let's go with it. Okay, very interesting. Again, the steps here are very fun. So you have two states here. So if you think about them as two sets, look at the set of all the states. You have Q0, Q1 here from model 1. You have Q2, Q3. These are the states. Take the cross product of these two sets. So you will have a new model which has Q0, Q2, right? It will also have Q0, Q3. This possibility, cross product, which means all possibilities will be there. All possibilities will be there. Similarly, you will have Q1, Q2. You will have Q1, Q3. We have 4 states now. Okay, we have 4 states. I'll tell you how to construct this model which accepts the intersection. We'll also see the union. First, I've constructed 4 states. Cool. Okay, what is the initial state here? Q0 is the initial state, Q2 is the initial state here. Now Q2, Q0 or Q0, Q2 here has this initial state and this initial state. So this becomes my initial state. First, I got 4 states. Look at this. First, I got 4 states, right? Once I got 4 states, now I'm defining my initial state. The way I'll define, again, this is AND, this is intersection. So my final state will be, what is the final state here? Q0. What is the final state here? Q2. So Q0, Q2 becomes my final state. Q0, Q2 becomes my final state. Okay, because it is AND. We'll also see if OR is there, what happens to the initial states, final states in the next example itself. Okay, now what about transitions? Q0 on A goes to Q1. Look at this. Q0 on A goes to Q1. So here Q2 is the same. Look at this. Q2 is the same here. So Q0 on A. So Q0 on A goes here because Q2 is the same here. I can't jump here or I can't jump here. For example, I don't want, again, this A. See, if you just ignore this Q2 because Q2 is same here, this graph I'll try to copy it here. Okay, this transition is here. Look at this. This transition is here. Now from Q1, again, this transition is also here. Again, look at this. From Q1, if you ignore the second one, if you ignore Q2 here, which is common between both of them, look at this, Q2 is common between both of these. So if you just ignore that, from Q1, from Q0 on A you go to Q1, from Q1 on A you go to Q0. That's what I've entered here. Now comes the interesting step, the very interesting step. On Q0, on B you go to Q0. But there is no element here which is Q0, Q0. There is no Q0, Q0, right? So let's hold on to that. Let's just hold on to that for a little while. Okay. So now if you look at this diagram, let's look at this again. Similarly, sorry, I forgot to mention this. Here Q3 is the same. So if you just ignore Q3, between Q0 and Q1, what do you have? A. So I'll just have A here. Look at this. The Q3 is the same here. So I can just ignore that. Similarly, between these two, Q0 is the same. So if I just ignore Q0, look at this. Q0 is the same. So I have Q2, Q3. Between Q2, Q3, what do I have? B here and B here. Right? So this has to be A. I'm sorry. This has to be A, not B. This has to be A, not B. My bad. Similarly, between these two, if you ignore Q1 here, the common one, you have Q2, Q3. Between Q2, Q3, how do you jump? Using B. Using B. Now if you notice here, from every state, from this state, transition A is there, transition B is there. From this state, transition A, transition B. From this state, transition A, transition B. From this state, transition A, transition B. Now if I label these states differently, if I call this as state A, if I call this as state B, if I call this as state C, right? Or let's just use the concept, if I use this as C, if I call this as D, right? So what do I have now? I have this state as A, which is also the final state. I have a state B, I have a state C, I have a state D. What do I have now? B this way, again B also this way, A here, again A backwards, A this way, and A backwards. Look at this. Look at all the steps that we have done. Again, the steps are very, very important. First, we took the cross product of all of them. We got 4 states. Okay, we got 4 states first. Next, whatever was the initial state here, Q0, Q2. So we named Q0, Q2 as an initial state. Because we have AND here, Q0, Q2. Q0 is the final state here, Q2 is the final state. So Q0, Q2 became my final state. Very good. So initial state done, final state done. Now all these transitions I have done by looking at, suppose if you look at Q0, Q2, Q1, Q2, right? So Q2 is common. So ignore Q2. Look at what are the transitions in these 2 diagrams between Q0 and Q1. You have this AA. That's why I've introduced these 2. So on and so forth. If I do it, I got the final automata. Right? So this is one way of constructing the intersection of these 2 languages. So this automata M accepts L. This automata accepts L, where L is the intersection of L1 and L2. This is one way to construct it. Again, you can construct many, many complex examples using this strategy. Again, this is AND, which means this is like intersection. What about union? Let's look at that example, right? Let's look at that example. So number of A's is even or number of B's is even. So if you think of this as language L1, L1 union L2. Same example here. So same M1 will be there, same M2 will be there. Look at this, same M1, same M2. But now how do I construct a language which is the union of both of them? Very similar steps to this, except one major change. Couple of major changes are here. Okay. Let's go with the couple of major changes. Okay. First, let's draw the initial and the final vertices or the final states change. The transitions, everything stays the same. So let me just redraw this again. Okay. Let me just draw that. So I have, again, my initial vertex. Let's keep the initial vertex and the final vertex a while, just for a second. So I have AB and I have CD. Okay. Let's write down all the transitions first. Okay. The transitions, everything stays the same. The way we computed the transitions here, same logic will compute it even when we have union. Nothing changes, right? So A, again, B. Similarly, here you have B. Here you have B. The transitions don't change, right? Now, if you look at both these diagrams, what is the initial state? Q0 here, Q2 here. You can only have one, you need to have one unique initial state. You can't have 2 initial states. That's not accepted in a finite automata. And you need to have one initial state. Without an initial state, an automata is not defined. So Q0, Q2, which is this state, which is equal to A. So we make A the initial state. Cool. Now comes the fun part. What about the final state? So the initial state for intersection and for union is the same. Initial state is the same. The final state is a tricky part. Here, what is the final state? Q0. Here, final state is Q2. Look at this. Q0, Q2. Now, amongst these 4 states, if it contains either Q0 or Q2, we'll call it a final state. So, for example, in this, we said it has to contain both Q0 and Q2. In the case of intersection, because it's logical AND. So it has to contain Q0 and Q2 for the final state. In the case of in the case of union, we'll say it has to contain either Q0 or Q2, because logically this is a logical OR. So of these 4 states, which states contain Q0 or Q2? This state A contains Q0 or Q2, B contains Q0 or Q2, C contains Q0 or Q2, D does not contain. So now what I'll make here is, I'll make this final state, I'll make this final state, I'll make this final state. Because this is nothing but Q0, Q2, right? And what is this? This is Q0, Q3, right? And what is this? Q1, Q2. Because my final states in the original machines, are Q0 and Q2, right? Because I'm constructing a logical OR, if it contains Q0 or Q2, I'll make it final states. So the only difference between logical AND or the set intersection and or set union. The only difference is in deciding final states. The initial states, it's the same thing. Just like in the previous example, initial states is the same thing. Final states concept changes. Okay. In this case, final state should contain the final state of this and the final state of this. In this case, final state of this or the final state of this in the case of union. Okay. All the transitions stay the same. Transitions stay the same. Only final states change between union and intersection. Right. Again, we'll see many more examples like this so that this concept is much more clear for you. Okay. So again, the minimum automata has 4 states here. Just FYI. Okay. Now let's look at this. Okay. So number of A's is even and number of B's is odd. Okay. Let's draw the automata for this. Okay. Very simple. Number of A's is even. Okay. This is my Q0. If I get an A, I go to B. I go to Q1. If I get an A, I go here, right? Again, if I get a B here, I'll be here. If I get a B here, I'll be here. This is my machine 1. And I have logical AND here, right? And number of B's is odd, right? Number of B's is odd. Again, number of A's is even, right? This same diagram. Number of B's is odd, changes slightly. Let's draw the number of B's, okay? So this is I'm trying to use different symbols. Q0, Q2, Q1 here, Q2, Q3. So if I get a B, I go to Q3. 1B, right? 2 B's, I go here, so on and so forth. If I get A's, I don't care. That's it. This is your machine 1, this is your machine 2. Let's construct the intersection of both the machines. So what all states will I have? Q0, Q2. Look at this, Q0, Q2, Q0, Q3, second state, Q1, Q2, right? Similarly, Q1, Q3, 4 states. Which is the initial state here? Q0, initial state Q2. So Q1, Q2 becomes my initial state because it is logical and, right? My bad. Yeah, the initial state is okay. What about the final state? Final state is Q0 here. Final state here is Q3. So Q0, Q3 becomes the final state now. Okay, because it is and. It has to be Q0 and Q3. So this becomes my final state. Okay, what about transitions? Very similar. If you notice these two, Q2 is the common part. Just ignore the Q2, you have Q0, Q1. The transitions are on A. So you get your A transitions here. Similarly, between these two, ignore Q0 because Q0 is common, you have Q2, Q3. Between Q2, Q3, you have transitions on B. Okay. Similarly, you will have transitions on A here. You will have transitions on B. That's it. That's it. Very simple. Very, very simple. Right? Now, obviously, if you want to change it slightly, if you want an OR here instead of an AND, look at this. If you want an OR instead of an AND, what do? You take the same diagram here. Same diagram. The only thing that will change here, as I told you earlier, is the final states. Okay, let me just draw the whole thing here quickly. So I have Q0, Q2. I have Q0, Q3. I have Q1, Q2. I have Q1, Q3. Right? Yes. So I have A. That's what I have, right? AA. Sorry, this is AA. My bad. AA. So this is also A. This is A. This is A. This is B. This is B. This is B. This is B. Right? Now, what are the final states here in this diagram? Q0 and Q3 are final states. Okay. In machine 1 final state is Q0. Machine 2's final state is Q3. So Q0 or Q3. So this could be my final state. This could be my final state. Q0 or Q3, right? That's what we have, right? Q0 or Q3. So this can't be final state. This can be final state because it has Q3. That's it. Everything stays the same. Only the final states change. In this case, the final state is only this state because you have Q0 and Q3. Here you have this or this, right? This model 1 or language 1 or language 2. Because you have OR, which means the union operation, right? That's how you get this. Very simple examples, right? Very, very simple examples. Now let's look at slightly more complicated examples. Slightly more complicated, nothing rocket science here. Okay. So let's again do this. Okay. You want the number of A's to be congruent to 0 mod 2, number of B's to be congruent to 0 mod 3. Let's construct the models here. And here you have and, right? So since it is mod 2, I just need 2 states. This is basically meaning even, right? So I have Q0, I have A, Q1, A, right? B here, B here. See, with practice, you can draw this in the middle of night also. It's that simple. Okay, you have mod 3 here, which means you need 3 states. Okay, so let's actually draw 3 states here. You have Q2, again, I don't want to use the same terminology here. So Q2, you have B, right? Q3, Q4, okay? Q2, Q3, Q4. Let's assume this is 0 Bs, 1 B and 2 Bs, okay? Just for simplicity, right? So now how does this work? This works like this, okay? If I get a B like this, again, we have seen how to draw this in the previous videos, right? A, that's it. Very simple. And of course, what is my final state here? Sorry, my final state is this. My final state is Q2. Now I want AND of both of them. So let's start constructing it. Sorry, my bad. So let's start constructing it. Okay. 2 states here, 3 states here. So I'll get total of 6 states. 2 into 3. Right. So 2 states here, 3 states here. Total of 6 states because it's a cross product. So let's actually write it down. Q0, Q2 is 1 state. Okay. Q0, Q3 is 1 state. Q0, Q4 is the 3rd state. Then let's assume Q1, Q2 is the 4th state. Q1, Q3, Q1, Q4. Okay. What is the initial state? Obviously Q0, Q2. This is my initial state. Because I have AND, what will be the final state? Q0 and Q2. So this becomes my final state. Till now everything is good. What about transitions? Again, let me show you transitions here. Okay. So if you notice these two, okay, Q2 is common. So Q0, Q1. Between Q0, Q1, you have transitions on A. So let's just draw transitions on A here. Similarly, Q3 is common. You have Q0, Q1. Sorry, my bad. I keep getting confused. AB, AA. Okay. So this is A. This is also A. Similarly, Q0, Q1. This is A and this is A. Cool. Now what about these two? Q2, Q3. Between Q2, Q3, what do you have? B transitions you have. Okay. This B transition. Look at this. This B transition is what you have. Okay. What about Q3 to Q4? You again have a B transition. This B transition is here. Okay. So this is also a B transition because Q1 is common. Q2, Q3. You have a B transition. Q3, Q4, you have a B transition. Now you have this also. Q4, Q2. Q4, Q2, you have this B transition. Okay. You have this B transition also. Look at this. That's all you have now. Okay. You have 6 states. You have 6 states now. Okay, let's actually label these states differently. Let's call this state as A. Let's call this as B. Let's call this as C, just for simplicity. Let's call this as D. Let's call this as E. Let's call this as F. Okay, so this is how I'm calling this. A, B, C, D, E, F. Now let's try something interesting. Can we minimize this further? Can we minimize this finite automata further? We don't know. Let's try that. There are some interesting strategies that we can discuss. Okay. So I'm calling this A, B, C, D, E, F. I have 6 states, right? So first thing that I do whenever I want to convert this into, whenever I'm trying to minimize, I first convert this from a graph to a transition table. This is my transition table. I have pre-drawn this. Okay. My initial state is A. My final state is also A. Okay. Look at this. My initial state is A. My final state is A. Because minimizing a finite automata using a transition graph or a transition diagram is much harder. It's much easier from the tabular form. Now, from this, can I somehow combine these states? Let's see. See, I cannot combine A with anything else. Okay. Look at this. Because A is a final state, nothing else is a final state. You can never combine a final state with non-final states. So A I can't combine. First lesson, A I cannot combine. Now let's try other pairs. Suppose if I try to combine CD, can I combine CD? If you look at C, this is your C, this is your D. If I want to combine CD into one state, okay, I should combine F and A into one state. I have to combine A and E into one state. But we just said a while back that A cannot be combined with any state, which means CD cannot be combined. Look at this. This is a very interesting strategy. Okay, this strategy again, there is a whole literature on how to minimize in an algorithmic sense. Okay, you can take each pair like this, very simple strategy, very commonsensical. Okay, let's take another example. Can I join B and C? Look at this. Can I combine B and C? Look at this. Can I combine B and C? Let's try. If I want to combine B and C, I have to combine E and F into one variable. Nothing stops me from that. There is no restriction. The only restriction as of now is A cannot be combined with them. Then I have to combine B and C also. Sorry, A and C also. This is not valid. I can't combine A and C because A is a final state and C is not a final state. So you can try many of these pairs. Look at this. Again, you can also try these things. Okay. If you try all the other pairs, if you try to combine all the possible pairs, you will encounter some block or other block. Okay. For this problem, you cannot go below 6 states, even if you try. Okay. Again, when you have it in a tabular form, it's much more easy to try to combine. And imagine if I'm combining B and C for some reason. Instead of writing B, I'll write it as BC. So I have one state BC, right? In the previous video, we saw for the modulo stuff, right? For R mod n, for congruency of R mod n, we have seen how to combine them using this table. This is another strategy where I try to pick every pair of states and I try to see if I can combine them. If there is any violation, I cannot combine them. For every combination, I try to combine them. I constantly try and do that. If this hits a roadblock, because the very fundamental fact here is a non-final state cannot be combined with a final state. Okay. So in other words, a final state cannot be combined with a non-final state. You cannot break this logic. And now if you try to keep merging them, again, one merge can lead to another merge, and so on and so forth. For example, let's take this example, right? Suppose I try to merge E and F. Okay. There is no A here, so no problem. If I have to merge E and F into one state, B and C have to be merged into one state. But we realize that B and C cannot be merged into one state just a while ago. Because if I merge B and C into one state, I have to merge A and C into one state, which is not allowed. So there could be two hop logics also like this. Similarly, EF cannot be merged. Because the moment I merge EF, I have to merge BC. And I can't merge BC because then I have to merge AC. Okay, look at all the complications, right? So you can use this type of strategy also to minimize the number of states. For this problem, you cannot go below 6 states, whatever you try, right? So let's see one more simple example at the very end, right? So again, we have seen this example, right, a while ago. Number of A's is 0 mod 2, number of B's is AND. We have seen the case of AND. What if I want the case of OR? So very simple. Everything looks the same except for the final states. Everything looks like the same. Okay, let me just draw this diagram quickly and then we'll come to it. Okay, how would that diagram look like? My A will be here, my B will be here, my C is here, my D is here, my E is here, my F is here. What are all the transitions here? My A here, again A here, same diagram. Okay, I almost know it by heart now. Transition B, this transition of B, right? That's what we had if I recall. Anyway, I'll just check that. B here, sorry, this is A, my bad. This is A, this is the transition B. Right? Now, that's what I have, right? B, A, yes. So what will be my initial state? Q0, Q2, which is A. So my initial state stays the same. What about my final state now? Look at this. Here, Q0 or Q2. So which all are Q0, Q2? A is Q0, Q2. B is Q0, Q2. C is Q0, Q2. Sorry, C is Q0, Q2. Yes. This is Q0, Q2. That's it. So A, B, C, D. All 4 of them can be final states here. A can be final state, B can be final state, C can be final state, D can be final state. Except E and F, everything else can be final state. Because I have the OR logic here. So I hope with these examples, right? With these examples, you have understood the concept of building compound automata with all these examples, and also how to compute the complement of a finite automata to solve problems much more elegantly.